Okay, hi everybody. Thank you for joining this session. Uh, Nitish, over to you. You can start the session.
Okay. Hello everyone. I am Nitish Deshpande. So I will briefly introduce myself. I graduated from IIT Kanpur in May 2021, that is last year, and I have been a coordinator of electronics club in my third year. So just before the COVID started, I was the coordinator, and currently I am at Institute University in Raleigh, and I'm pursuing PhD in wireless communication in Professor Robert Heath's group. As you can see that this is the for our organization 6G which is 6G North Carolina. So yeah, so before I start, has anyone heard of this recent news of the clash between this 5G industry and the aviation industry? So if anyone has like heard of this recent news, can you unmute yourself and tell me about like what do you know about this recent news? So are participants allowed to unmute themselves and like discuss, or is it only?
Yeah, I have changed the settings. They can unmute themselves now.
Yes, I heard about it on the news.
Yeah, can you briefly describe like what you heard about it?
Like I don't know too much, but like it interferes with I think the aircraft communication. I don't know much about it at all. So
Okay, anyone
Yes,
else wants to say
yes, I
something?
can give an answer for this.
Okay.
So currently in the United States, Ericsson is responsible for setting up the 5G network over there. So it's over the safety concerns because aviation industry has seen many technical issues regarding due to like networking systems. That's why even the aeroplane mode was made. So they are raising issues that since the microwave 5G is going into like how can I explain the gigahertz range, right?
Okay.
So that can cause a lot of problems with the aviation system, the aeronautical system.
Okay. Okay. Yeah, I think you are very close. So I will give a precise answer of what's the issue. So yeah, that's how I'm going to start, and that's how like I will show like how relevant it is to this current topic of filter design in microwave circuits. So yeah. mm, So can you see my screen, everyone?
Yes, it's visible. It's visible.
Okay. Yeah. So this is there was this recent news of this clash of the 5G industry and the aviation industry. So what happens is that in this aeroplane you have this altimeter, which is a radar. It sends out a signal and reflects from the ground to calculate the height of the plane from the ground, right? And these instruments operate in the range of 4.2 to 44 gigahertz range. And currently the issue is that the 5G signals also have a similar spectrum. So here you can see that this is the 5G band, which currently AT&T and Verizon they are using, and as you can see that there is some spurious emission level outside the desired range, and the altimeter spectrum ideally it should be in this range, but you can see that since there is a perfect bandpass filter is not possible, so there is some overlap between these two spectrums. So what happens is that the power from the 5G signal can interfere with the signals in this spectrum, which is called as the adjacent channel interference. So since these altimeters they are very old devices, like they were designed in the 1920s, so they are not that sophisticated to handle this adjacent channel interference, and that's why recently, like since the new spectrum of 5G has started, um, they are not able to mitigate this interference due to the low quality filters in these devices. So one solution is like to change all those filters in all altimeters. But it's not like a one-day solution. It would take some time, and there are many financial reasons for which they are not currently doing. So that's why the 5G industry, they are forced to limit their spectrum so that there is no channel interference from with this spectrum. And yeah, this is the immediate solution which has been enforced right now. Like they should limit their spectrum. And other solution that is proposed is that the strength of the 5G signals near airports can be reduced, or the antennas can be directed towards the ground so that when the plane lands or takes off, there is no interference with the altimeter signal here. So yeah. So like the technical solution is very simple, but the reason they are not doing it is because of these financial reasons. Technically, we should just design a very good bandpass filter, and that's what we will discuss in this talk today. Okay. So can anyone tell me like what do you understand by a microwave? Like uh, everyone must have heard this signal, like this term microwave. So can anyone tell what do you mean by it? So one thing that like everyone has in their home is an appliance for rapidly heating food, and that is called microwave. But this is not the exact definition of microwave. The exact definition is it describes a circuit that is large compared to the RF wavelength, which is typically 1/20th fraction of the wavelength. So if the circuit is of this order, length of the circuit, then we call it to be in the microwave regime. And till now, you must have been only introduced to the lumped circuit, which is this one. That is, we have some nodes and there is some voltage and then resistors and inductors, capacitors in this kind of circuit. But in the microwave regime, what we use in place of circuits is a distributed element, which is called as a transmission line. So since the length is comparable to the wavelength, it takes time for the signal to propagate through this circuit. So you can see that the signal may look different in different places. And this is known as the distributed effect of microwave. So here you can see that the voltage is function of time alone, and in the distributed circuits, the voltage is function of time as well as space. So there is one extra variable here. Let's say this is one dimension, so just x variable, but in practice it can be any dimension. So it's function of time as well as space. And here, till now, we have only been introduced to circuits which are a function of time. So let's look at how things change with the microwave circuits. So some applications of microwave circuits. So this is the breakout of the iPhone 13 PCB. You can see that there are many chips involved here and operating in the millimeter wave region. And yeah, I just labeled some of the like companies which are working in this area, like the Skyworks, Qualcomm, and Qorvo. So these companies, they manufacture these chips which are present in this iPhone 13. And yeah, another application like which I think at your level you can like you do in the club is the IoT devices. So you must have seen this kind of device in the club. So even this has like this has to communicate with some controller through wireless communication protocol. So there are some antennas and some kind of RF processing here in this board. But the difference is that this is very low power as compared to some applications like radar, which are used, let's say civilian radar is used for weather forecast, and military radar for defense purposes, and even for space and remote sensing, we have radar. So these require a lot of power, but there are some low power devices, low power RF communication, which is energy efficient, and so lots of applications of microwave circuits. So, this is a simple block diagram of how the circuit looks inside in your phone. So this is like a very simple circuit, which is the transmitter block diagram, and this is the receiver. So here you have this antenna. This is the power amplifier, bandpass filter. Then we have um, a mixer which mixes the intermediate frequency with the carrier signal, and then there is modulation here. So today we are going to focus on design of these filters, which is bandpass filter here. So the application of bandpass filter in this block diagram is to remove the image carrier. So you must have studied like when we have the modulation of some signal, right? There are like two components. So let's say if you have a sine function, like generally this is a sine or cosine function here. So you must have studied that the Fourier transform of a sine function is two impulses, right? So when you modulate it, you will get two um, impulses in the frequency domain, and that's what I'm calling as the image. So we just need to consider one carrier and bypass the second carrier, right? That's why bandpass filter is very important in this block diagram. Similarly, this receiver, we have this bandpass filter here. So as you saw in the previous application that we need bandpass filters in this kind of setup, right? So this is like a receiver here. So we have bandpass filters to remove the out of band signals, and even low pass filter to remove images. Yeah. The filters are a very important component of the radio system. So now let's go back to the transmission line definition. That is the like why do we need transmission line, and why how is it different from the lumped elements? So you can see that the energy in the transmission line is carried in the form of electric and magnetic fields. So this is the current, and from Maxwell equations, you must have studied that this is the electric field and magnetic field. They are perpendicular to this current, and you can see that there is common ground here. So the like in PCB, you have a common substrate, and that's where the return current uh, passes. So this is like a complete circuit. Yeah. This is the setup, like how it looks in practice. So you have one conductor here, and there is a dielectric, and it is defined by some parameters like thickness of the conductor, width of the conductor, and height of the substrate. And this is the relative permittivity of the microstrip line. In terms of circuit symbol, it's just like this. And in terms of resistors, capacitors, inductors, it's this one. So resistor, inductor, capacitor, and this is the conductance, which is reciprocal of resistance. So this entire thing can be modeled using just lumped elements. So piecewise, you can apply the lumped elements so that when you cascade many such models, you get this transmission line. So this model is governed by some mathematical equations, which is known as the Telegraph Equation, and this is in phasor form, right? So you can see that the voltage here depends on the current, and the current here depends on the voltage. So this is a second order differential equation, right? So can anyone tell me like what kind of solution you would expect to this kind of equation? I think most of you are in your first or second year, right? So if someone of you has completed the differential equation course, I think you might be able to guess the solution of this equation, right? Can anyone suggest something like what kind of solution you would expect? Hmm?
Sine and cosine.
Yeah.
Yeah, basically it's uh, a traveling wave, like superposition of two waves. So this is a forward traveling wave, and this is a reverse traveling wave, and even the current follows the same expression. So if you plug this expression in this differential equation, you will see that yeah, this gets satisfied. So essentially it's the derivative of this expression equals the current expression here, right? So you can verify this, and this V0 plus and V0 minus, these are the amplitudes of the voltage. So this is the amplitude of the forward traveling wave, and this is the amplitude of the reverse traveling wave, right? And yeah, this gamma factor depends on this RLGC parameters, which is given by this expression here. It's a complex number, so the real part is the attenuation constant, and the imaginary part is the phase constant. And then there are some other quantities defined here for this transmission line, which is the characteristic impedance, which is a ratio of this R plus J omega L by gamma. And in terms of RLGC, it's this one, and it depends on the frequency of also like the operation frequency of this transmission line. Yeah, so this is basically the crux of transmission line, and now we will see different applications like how it can be used in the circuits. So let's say we have some load here, and we are observing from this point. So this is like the input impedance, and we want to given this load, we want to find the input impedance at this point. So the expression for this is given as this one. So now, like, there are multiple things to understand here. So gamma L is the voltage reflection coefficient, which is amplitude ratio of the voltages of reverse and forward traveling wave. So essentially, gamma L is just V0 plus by V0 minus here, and sorry, reverse versus forward, right? So V0 minus by V0 plus, and beta L is the L is the length of this transmission line, and beta is basically the wave number here, wave number times the length, and beta L is known as the electrical length of the transmission line. You can see that there is factor of 2 here. The factor of 2 is because the wave travels from this point to this and then reflects back to this point, right? So that's why there is twice the phase shift to account for the round trip of the wave. Now we have some parameters like the length and this load coefficient, right? The voltage reflection coefficient. So varying these two parameters, we can get different values for the input impedance here. So let's see, like if we keep the load like infinity, like let's take ZL is infinity, so it's an open circuit. So if you plug the expression like ZL equal to infinity here, so you will end up with this expression, which is which depends on the electrical length, and this can replicate a capacitor. Like this input impedance can replicate the impedance of a capacitor, which is this one. And if we take ZL as 0 here, which is short circuit, so it can replicate a inductor, right? So now, like we can map this transmission line concept to the lumped element. So it is very crucial to understand this this expression here. So using this, we can get different values for the input impedance. And then there is special kind of setup, which is quarter wave transformer. So if you see that we have this expression tan beta, right? And um, if we have the length of this as lambda by 4, so yeah, twice lambda by 4 is lambda by yeah, since we have a 2 beta, so we will get this in degrees as 90 degrees, and then this reduces to this expression here. So the special thing about this expression is that you can see that ZL is in the denominator of this, and it's like Zn is inversely proportional to the load impedance. So if you have a very small resistance here, you can observe that at this end, you will observe a very high impedance. So it's like essentially transforming a very low impedance to a very high impedance. And yeah, you can change the small capacitor into a large inductor. So these kind of applications are very interesting, like with the transmission line, that just adjusting the length of this transmission line and appropriately selecting the load, you can get a desired impedance here. So let's see how we can use this concept to design some filters. Okay. So is everyone familiar with the basic kind of filters that we have, like low pass, band pass, high pass, and band stop? So these are like hello. you want to say something? Okay. So basically, like a low pass blocks the low frequencies, and high pass blocks the high frequencies, and band pass is like there are two cutoff frequencies here, and band stop also like two cutoff frequencies here. But every filter design process starts with designing a low pass filter, and then we can convert or map this low pass filter by some transformations to a band pass, high pass, and band stop filter. So let's first start with the filter selection and transfer function design. Then we go to the low pass prototype design. Then we apply some frequency, impedance, and bandwidth transformation, some more element transformation, and then we have the final circuit tuning, right? So now our goal is to design a bandpass filter. So the specifications that we have is there is a central frequency 17 gigahertz. Then there are two cutoff frequencies. The first is -3 dB frequency, where so is everyone familiar with this decibel convention? If not, you can tell me, like if someone doesn't understand what this decibel means. Okay, so basically -3 dB is just the half of this amplitude. So if you uh, plug in 10 log half, so you will get -3 here. And then similarly, the attenuation at this is -20 dB. So we consider the 2 points where we have this cutoff frequencies, which is -3 dB point and -20 dB point. So these specifications are given to us, and we are to design the filter, the circuit for this filter. Okay. So yeah, any questions till now? Like if anything is not clear, you can ask. Okay. I will proceed to the next slide. So we have this input and output relationship, which is governed by the transfer function here, which is y s by xs. So s, like this equation is in the Laplace domain, which is the frequency domain. So we have this transfer function, and first we would start with converting this bandpass desired response to a low pass desired response, and then apply some frequency scaling. So what we do is we have the standard template where we have cutoff frequency as 1 radian per second, and we fix the cutoff frequency of the 3 dB point to 1 radian per second. So we want to map this frequency here to this low pass response. So you can see that the difference here between the frequencies is 1.7 gigahertz, and even here it is 1.7 gigahertz. So accordingly, we get when we scale down 17 gigahertz to 0, when we like just translate along the frequency axis and then scale it to this, we get 1 radian per second and 2 radian per second here. And now this standard low pass response has this transfer function. We will select the Butterworth filter, which is given by this expression there. As you can see that there are only poles here, so it's known as a all pole response. And okay, now we have this expression, and n here is the order of this polynomial here. So we want to find a suitable order to satisfy this this response. So we try different filter orders. So n equal to 1, we compute the attenuation at 2 radian per second. So we see that it's just -6.9, and it's not sufficient attenuation. And we need to go up to order 4 circuit to get a attenuation of more than -20 dB, right? So order 4 is the nearest smallest possible order for which we can get attenuation at 2 radian per second more than 20 dB, right? So that's why we select the order of the circuit as n equal to 4. Now, once we have set the order of the filter, we need to extract the circuit element from this transfer function. So an important relation here is the relation of transfer function and the reflection coefficient. And from this reflection coefficient, we get the expression for the input impedance here. Now, the input impedance would be also a function of S. We want to get the circuit parameters, in terms of capacitor and inductors, using this expression for input impedance as a function of the frequency. So you almost be knowing that the impedance of a capacitor is in terms of this Laplace S is 1 by SC, and for inductor it's like basically 1 by j omega L, and for inductor 1 by j omega C, and for inductor it's j omega L. So using these two relations, we try to get the capacitance and inductor values. So we start with the like, let's say we have two nodes here. We start with at this point, looking at from this point we observe the input impedance, and if this input impedance has a pole at S equal to 0, we can extract the capacitor from this circuit, and then once we extract this capacitor in series, we can subtract that and get the residual input impedance. So we repeat this process until we don't have any poles or zeros. So the trick here is like you can either extract a series, a capacitor or an inductor, or a series, a parallel inductor or capacitor. And if you are extracting series inductor capacitor, you have to work with the expression for the impedance. And if you are extracting in a shunt capacitor and inductor, you have to work with the expression for admittance. So admittance is just reciprocal of this input impedance. So now we apply this to this transfer function here, and I won't go through the steps of doing it for order 4, but it's already been done by someone, and we know the expression for the coefficient, the values for the inductor and capacitor that we need to use. So it's given by this expression here. So there are two kinds of circuits possible. So if you start with extracting an inductor first, we'll get this LC ladder here. And if you start by extracting a shunt capacitor first, you will get another type of LC ladder, but both essentially give the same transfer function. So can anyone tell me like how does this give a intuition of this circuit giving a low pass filter? Like, just a quick check that this can pass low frequencies. I think you must have learned it in your VHC 201 course, or if someone is from the first year, I think you might have learned during your physics courses in standard 12th, I guess. Can anyone tell me the intuition, like a quick check to how to check whether this is a low pass filter or not? Hi,
We attach a battery to it. DC voltage.
Yeah, correct. So you know that the capacitor blocks DC current, right? But since this capacitor is in like in both the circuits, capacitor is in a shunt, so it won't it won't block the DC current. So it will essentially allow the low frequencies to pass. Okay. So now can anyone suggest me some transformation to transform this low pass circuit to a band pass circuit? You know the band pass circuit is like you have some you block very low frequencies and you block very high frequencies, and you just allow frequencies within a certain range. So what modification would you propose to this circuit to get a band pass circuit? Any suggestions?
Put inductor in shunt and capacitor series?
If you do that, then won't it result in a high pass filter?
Put what I said in series with this thing.
Kind of, yeah. I think you're on the right direction. But can you just suggest a very simple trick? Like, what should I replace this inductor by, and what should I replace this capacitor by? Like a very simple modification. I think we're on the right track. You said that you put this in series with the inversion of this, right?
Yeah.
Yeah, it's correct. So what you do is you replace this inductor by one inductor in series with one capacitor. So just this inductor you can replace with, of course, the value would change. The value would depend on the cutoff frequencies, but you replace this inductor with inductor and a series capacitor, and this capacitor you replace by a shunt capacitor and a shunt inductor. So what happens is that for very low frequencies, since we have 1 by j omega c as the capacitor here, right? So if omega is 0, so this would be infinite impedance here. So this would block very this would block very low frequencies, and if frequency is, let's say, infinity, so inductor would have the infinite impedance. So here we are blocking very high and very low frequencies, and when we have in shunt, if we have a shunt inductor and shunt capacitor, so in terms of admittance, it would just be the opposite thing, and you can see that this would result in a bandpass filter, right? But in practice, it is difficult to realize the series elements using transmission line. So can anyone suggest, like, what should we do to transform this series inductor to a shunt capacitor? I just covered it in the previous slide, so I think, yeah, if you try to recall and if you're paying attention, I think you should get it. Like, what should I do here to replace this series inductor by a shunt capacitor? Anyone? Sure. Can anyone suggest something like how should we transform this inductor to a shunt capacitor? Okay, it's very simple. You just use a impedance inverter here. So this is basically one device which can replace this series inductor to a shunt capacitor, and of course there are some other elements, like there is some phase change here, but we don't care about the phase change because we're only concerned right now about the magnitude response and not the phase response. So you can replace this inductor by a shunt capacitor and two input impedance inverters and a phase transformer. And now we use this replacement in our circuit. And then, as I discussed earlier, the inversion of this low pass to band pass has replaced this series inductor by someone in the chat, I think. Shivam Roy, what's your question? Can you unmute yourself and
I am finding it difficult to understand whatever is going on. So, is there anything or any theory that I have to learn before understanding these things?
so you are in your first year or second? I think you are first.
I am in my first year.
Okay. Okay. Have you learned AC circuits in your physics, like JE physics?
A little bit, not in great depth.
Okay. So I think these concepts are right from that. I didn't cover anything new. Like I think you must have understood the AC circuits, right? There was one chapter on AC circuits where we use series RLC and parallel RLC. So those are just concepts from that topic. I haven't introduced anything new here.
Okay.
Maybe you can revisit those concepts. But once you go to second year, you will have this ESC 201 course. So I think everyone from second year would be able to follow it. So yeah, don't worry if you don't understand it right now. In your third semester or fourth semester, you will have this electronics course. It's compulsory for all. So yeah, I think you will be able to understand it during that course. So they will revisit the RLC circuits again. So yeah, but you can also revisit your JE physics to understand this concept.
Okay. Thanks.
Yeah, I think it might be a bit difficult right now for the first year students to grasp all these concepts. But yeah, if you have studied well those RLC circuits in your physics, so yeah, some of you might be able to grasp it. Even the electronics club would cover some, I think, a winter workshop or something. Yeah, winter camp. Are you conducting the winter camp? I think they cover this in the winter camp, right? The basic filter design. Uh, did the coordinators cover? Like, Neza Prakar?
Yeah, so like for Y21, the winter camp has not yet taken place. Y20, we covered this stuff, the basic analog filters.
Okay. Yeah, I think Y21 came a bit late, right? Due to COVID. So yeah, they might have missed the winter camp. But generally, like everyone from first year, like in my first year, they had covered it during the winter camp, just after the first semester. Okay, so where were we? Like, yeah, so to replace this series inductor by a series inductor and capacitor, and the values for this depend on the corner frequencies. These are the band edge frequencies that we have from the response, and the capacitor can be replaced by a shunt inductor and a shunt capacitor, and values for this are given by this expression. So omega naught here is the center frequency. So in our case, it's 17 gigahertz times 2 pi, and omega 1 and omega 2, they are 15.3 times 2 pi, and 2 pi because omega is 2 pi f, so 18.7 times 2 pi. So we have this corner frequencies here, and then there is this factor alpha, which is what we call as the fractional bandwidth. It's the ratio of the inverse of the fractional bandwidth, because it's ratio of the carrier frequency and the bandwidth. And now one more thing that we need to do here is to transform the impedance scaling, and the because here we have assumed that everything is this RL and RS, they are 1 ohm, but we need to scale it to 50 ohm, which is the standard used in most of the microwave circuits. So the rule for impedance transformation is you multiply the inductor by the value Z0, which is 50 ohms. And yeah, you have some question. Manu, you raised your hand.
No, that was by mistake.
Okay. And the capacitor, you divide by the impedance, because yeah, you must have studied that XL is omega L and XC is 1 by XL is j omega L and X is 1 by j omega C. So that's why there is a reciprocal here. And then this impedance inverter is just scale this K by KZ naught. Now using this transformation, we get this circuit here. Now we have this replacement. So instead of ladder LC, we have converted this to shunt capacitor and then transformed the capacitor to a shunt inductor capacitor. So now we have this circuit here, and we simulate this circuit in AWR. We get this response. So you can see that it is almost matching the desired response, that this is close to 17 gigahertz and 15.3 and 18.7. And these points satisfy the minus 20 dB attenuation. So now we have to move from the lumped element to transmission line. So can anyone suggest any replacement for this LC parallel circuit here? How do we realize this using transmission lines? Any suggestions like how to replace this with transmission line? Okay, what happens to this LC parallel thing at the resonant frequency? Resonant frequency is omega not equal to 1 by square root LC. So if you put omega at this, you set the frequency at the resonant frequency, this would be an open circuit, right? Because the impedance of the capacitor would cancel the impedance of the inductor. So this would essentially be an open circuit. So to realize an open circuit, what we do is we use a short circuited stub with the quarter wave transformer. So previously we studied that a quarter wave transformer can transform a short circuit to an open circuit. So if we make RL0 here, we would get an open circuit here because it's just the reciprocal of the resistance at the load. So if we have a zero load here, then we would get infinite input impedance here. And the value for this comes from the first order approximation that you differentiate the expression for the impedance here and with the transmission line, and then you equate both of them for other frequencies. And I won't go into the maths of this, but yeah, if you, this is an approximation, this is not an exact result. So you get the characteristic impedance of the transmission line by replacing this LC resonator here. And then this impedance inverter you can replace with another transmission line, which is the quarter wave transformer of 50 ohms, which we also discussed previously here, that this thing. So just replace, like this can be used to realize the impedance inverter, because the expression is similar, right? Zn is Z01 square by ZL, and this thing here was Zn is K square by ZL. So K is the characteristic impedance of the transmission line, and you can just replace this by the quarter wave transformer. Now we have replaced all these elements with ideal transmission line, and you can see that in the first iteration, once we convert from this circuit to this circuit, the response does not exactly match the desired response. There is some difference in the cutoff frequencies. That is because, as I said, this is an approximation, so we won't get the exact response. What we do is we have to do some scaling for this transmission line. We can scale the C and L values. So as you see that the value of C depends on this factor alpha, and alpha is inversely proportional to the bandwidth. So what we can do is we can observe the bandwidth here and try to accordingly scale the bandwidth to the desired value. And then we change the values of L and C. And from the L and C, we change the value of Y0, which is changing the characteristic admittance or impedance of this transmission line. So currently we are set all this to 50, but we can change this. So now we have, let's say 10.3 and a different value here depending on the L and C here. And it took 3 iterations to get the desired response. Now we would convert the ideal transmission line to the microstrip, which is a realistic transmission line using the AWR software, which can model the non-ideal effects in the transmission line. So this is the microstrip, and to map the impedance, currently only this model only depends on the impedance of the transmission line, which is the characteristic impedance, 50 ohms. So there is some relation between the impedance and the width to height ratio. So for a given value of impedance and the permittivity of the dielectric, we can get width to height ratio for the microstrip. So now once we have this design, we can just plug in the value of the impedance and the permittivity that we are going to use for the dielectric to get the width to height ratio of this microstrip here. And you can see that this response is not very ideal. So there are some, it's not exactly flat, and the slope is different on this side compared to this side. So this is because this microstrip has some loss factor, which is called as the loss tangent. So due to some non-ideal effects, we don't get the symmetric response. But you can see that this is well within the specification. So we are the desired was 17 gigahertz, and we are getting 17.05, which is like very small difference, and even the cutoff frequencies are very close. So whenever you design, you don't need to get the exact parameters, but there are some threshold set by the in your design which you need to satisfy. Okay. So I will now demonstrate this simulation in the AWR software. So does anyone have any questions on the concepts covered till now? Or I think second year students might be able to follow the like this because they are already covered in the ESC 201, the lumped elements, and I think the third year students, I think Prakhar and Nessa, I think you might be doing the E340 course, right? So in that course, you will study the transmission line. Are you doing this course in your sixth semester?
Yeah, we are doing this course in semester only.
Yeah. So have they started this transmission line theory, or is it?
Yeah, they have.
Okay. So you might have understood most of the concepts, right?
Yes, yes.
Okay. Yeah. So in E340, they won't cover the circuit design part. So they will just cover like these concepts, like the telegraph equation and this quarter transformer, but the circuit design part, I think they won't cover. So it's what I learned here in this course which I took last semester, where they use this transmission line to design the microwave circuits. Now I will just switch to another device, and I will demonstrate the AWR software which I had used. Can you see my screen?
Yes.
Just hold on for a second. So this is the. I think there is some problem. Okay. This is the order 3 circuit, and just for simulation, I will show that this order 3 circuit does not satisfy the 3 dB cutoff and center frequency. So you can see that the center frequency here is 16.68 gigahertz, but it is very far away from the 17 gigahertz range that we need. So that's why we go to order 4 low pass filter, which is this one. So in the software, you can change the different values here, like the values that we computed from the expression that we have here. That is the Butterworth template. So you can plug in the values here and even change the values. And right now I set this to 1 ohm. But if I change it to 50 ohm, which is the scaled value to 50, I will get the same response. So the response for this is so this is well within the desired range, and now we have the ideal transmission line here, which is this one. For this, I have used the coax cable, and you can set the characteristic impedance here and the electrical length. So since it's a quarter wave transformer, I have used the electrical length as 90 degrees, and frequency at which this length is specified. So that is 17 gigahertz, which is our center frequency. Similarly for other transmission lines, so here it's not 50 ohm but 10.3 here, and for this it's 4.27. So can anyone tell me why the impedance for this and this is same, like, and even this and this is same? Like, why is there symmetry in this? Why do we have symmetry in this in these parameters? Essentially, it's because of this sine function there. So sine is, since it's a symmetric function, so if we plug in let's say r equal to 1 or 4, we will get the same value because it's a sine function, so it's a symmetric function. That's why we end up getting symmetric values for this Butterworth filter. But if you tune in this, if you change the values and make it non-symmetric, so it won't be a symmetric response that you are getting here. It would be something different. And then we have this ideal transmission line, and after 3 iterations, we get the desired response. So to get the desired response, I had to change the values of the impedance here. So now it's 10.31 here, but here I changed it to 11.9. So the scaling of this was because of the bandwidth. So I observed the bandwidth of this response and scaled it by that value. So it's actually inversely proportional to this bandwidth. So I just divided by this and multiplied by the uh, desired bandwidth, which is 3.4 gigahertz. And then applying this scaling to the impedance parameters, I got the desired response in this. This is the desired response. And then I went to this real microstrip line. So here we have two parameters. So this is the conductor, which is we have the width, length, and the substrate definition. So the width and length is as per this. So here we have four parameters. So the thickness of the conductor, width of the conductor, height of this dielectric, and the permittivity. So here we specify the width and length of this conductor, and this is the substrate. So here we specify the substrate thickness and this is the dielectric constant for this model. Sorry, so this is the relative permittivity, which is 4.6, and nominal relativity. I don't know what's this, but it's set to default. But we only care about this value 4.6 and the height of the substrate. Thickness is set by default, so it doesn't affect the equations. But our equations depends mostly on the height of this substrate and the width of this conductor. So we saw that W by H ratio defines the characteristic impedance of the transmission line. And then in reality, we cannot have an ideal short circuit. So we have this cylindrical via which can replicate a short circuit. But since we are using this via here, so it models the non-ideal effects, which we didn't have here. Like here, we were using an ideal short circuit, but now we have this this via which replicates a short circuit, but it's non-ideal effect. So that's why we are getting the response like this, which is not exactly symmetric. There is the slopes here are different, but you see the values are very close. And one more thing to notice is that here we are getting minus 4.32 and minus 1.32 here. So earlier we were getting the peak was 0 dB, but there is slight difference here. That is because of this factor here, which is the loss tangent. So there is this loss tangent of the dielectric. So there is some loss in the dielectric, and this loss tangent is basically depends on the material properties. So this dielectric would have some properties which defines the loss tangent. That's why we are observing some difference in the desired response. That is, there is some decrement from the 0 dB in this point. But this circuit, this response fits well within the tolerance values, which was like, I think, yeah, like this is very close to 17 gigahertz, and this is also very close to 15.3 and 18.7. So what we would say is that we are this is the best possible circuit giving us the response close to the bandpass desired response. So any questions about the software here? So you can ask questions about the concepts in this lecture as well as the any questions of using how to use this software and what else like uh, like how can you study these micro circuits on your own. So if you have any questions about that, you can feel free to ask about it.
Excuse me.
Right.
Yeah. So if you want to start learning about microwave circuits, like I'm a complete beginner, so where can I start to learn about it?
You're in your first year or second year?
No, I'm in my second year. So
Okay. So you have done ESC 201, right?
yeah.
Okay. So I think you can start like there is this book of Michael Steer. So these are the links to the different volumes. So the course which I learned last semester, it covered this volume 1, transmission line volume 2, and yeah, first 4 volume basically. And the concepts covered today were mostly from the modules, and filter design part is in this volume. So I will share the link in chat. So this is what I referred for this course here. Let me share this in the chat.
Yeah.
So, and if you are from electrical, so you will learn this, you will have this course, the EM course in your 6th semester, which is EE340.
Okay. Yeah. What course did you say?
EE340.
Okay.
But it will cover very fundamental concepts. Like it will focus mostly on the transmission line, which is like basically this slide which I had here, right? So it will just cover these equations, Telegraph Equation, and just solve some problems. But the circuit design part, I think they won't teach you in that course. You will have to take some more advanced courses. I don't know which course in IITK covers that, but here I had this EC 549 insisted course. So in this course, they covered everything.
Oh. Okay. Yeah.
Okay.
Yeah.
More questions?
Thanks.
So you guys must be studying the C340, right? NASA, Prakhar, and Shivam. Like, how are you finding this course currently?
Like we have just started, like we have what, 2 to 3 weeks of content we have covered. So up till now we have just done the telegrapher equations and how to read the Smith chart and things like that. So
I think the more interesting part is this filter design and the circuit design, which they won't cover. They will just cover some basic theory and using Smith chart, but they don't cover anything like using some software for simulation. And you can learn it on your own. And if you're interested, you can even introduce it in the club, like some summer project or some long-term project that you can introduce with this software, and also follow the books from Michael Steer. And if you're interested, you can start this in the club. It's a very emerging field in wireless, and as you saw the application, like it's used almost everywhere in the millimeter wave and different radar application and communication application. So it's a good domain. Like till now, we didn't do any project in the microwave and RF domain, right? So maybe we can start something.
Okay. Like we can work with some long-term project on this. I think.
Yeah. I think even this filter design is a very good project like for beginners because I also did this in last semester. It was like a 3-week course project, so it took almost 3 weeks to like write a very long report. So I will just show. This was the kind of report we had to submit for this course project. So it includes everything, like filter design and the different steps that I showed you today. So I can share this report with you if you want, and we can start something similar like filter design using this AWR software or any similar software. So